here's the flow metering data that you took at Crowden Great Book on the 8th of October. You've got the distance measurements that are then turned into areas, and then you've got a set of triplicate velocity measurements that you turn into an average, and then you multiply the velocities by the areas to give you the discharge in each panel, and then sum them to get the total discharge. You also need to carry the errors. So we've got the width and the depth. I've assumed that there's a 1 centimetre error on any of the measurements, the distance measurements. The error's probably less than this, but when the water's turbulent and you're measuring the depth, the water moves up and down a bit. And similarly, when you stretch the tape across the river, it's not exactly vertical. If it's not exactly horizontal, then there's errors because of that. So I've put down an assumed error of 1 centimetre on each of these measurements. It's not as a percentage of the measurement, it's actually a 1 centimetre error. And largely that's also because of the resolution of the tape as well. Anyway, so multiplying the width by the depth will give you the area. However, it's a little bit more complicated because of the shape of the channel, and that's plotted over here. So these charts are plotting the width against the depth and reversing the y-axis, so it actually looks like a channel. And you can see then that the areas of each of the panels will generally include a rectangular area and a triangular area underneath. So the formula that's in there is just working out the area of a rectangle and adding the area of a triangle. You don't need to do that, that's already written in for you. The errors that are worked out on those are a standard way of working out an error when you multiply two numbers together. So you can have a quick look. In the heart of it, you have the error, so C16 is an error divided by the number itself. So C16 divided by B16, so the error divided by the number squared plus the error divided by the number squared, and then we take the square root. So similar to what you do when you're adding two errors together. And then the final thing is that you multiply that whole amount, which is called the fractional error. You multiply that by the resultant quantity. The resultant quantity, F16, is the area. So that's the standard way of carrying the error when you multiply two numbers together. Now in fact, in this case, it should be a little bit more complicated because you're not just working out the area of a rectangle, you're also working out the area of that triangle as well, but I've disregarded that in this case. It's minor, you don't need to go into that. But you'll need to use this formula again when you multiply the area by the velocity. So you've got three sets of velocity measurements that were notionally taken at exactly the same places in terms of width and depth. They aren't exactly the same number, so that's partly to do with not being able to locate in exactly the same position with regard to width and depth, and also there may be some slight temporal variability in the velocity. Rivers do actually pulse. It's not necessarily to do with the discharge changing overall. There's no extra water entering the system, but they actually pulse. Anyway, there's some error, and you've been able to detect that by making multiple measurements of the discharge. So the first thing that you need to do then is to work out the average velocity. So we'll enter average. It's the average of these three numbers. And copy that down. So you've got your average velocity. The error on your average is the standard error of the mean. So in order to get that, we need to do the standard deviation. It's not standard deviation P, it's just standard deviation, because these are a sample of all the possible measurements you could have made. Standard deviation of these three numbers multiplied by a d value, but in fact it's a small sample size, it's a t value, and we get the t value for using the t inverse function, and the arguments that it requires are the probability, which is 0.05, we're working at 95%. The degrees of freedom is n minus 1, n is 3, so n minus 1 is 2, so we'll put 2 in. And then we also need to multiply this by the square root of the number in the sample, because we're working out the standard error of a mean. So the number in the sample is 3, and square root is raised to the power of 0.5. Of course that's 0, because our reading is 0, but if we copy that down, then we get our errors on our mean velocities as well. And then in this column we need to multiply for each of these panels. We've got these panels. For each of these panels we've got now an area and we've got a velocity. We multiply the area and the velocity together. Look at the units. Area is meters squared, velocity is meters per second, so we're going to get meters cubed per second. So area multiplied by velocity, which is 0 in this case, so no velocity, no discharge. But there we go, we've got our discharges. That's the discharge in each panel. The total discharge, of course, is going to be the sum of all those panels. And then the error, we're multiplying two numbers together. The numbers we're multiplying together are the area and the velocity. Each of those has an error. So we can come back and make sure the brackets are right, but we'll start off with sum. We need to multiply, we need to divide the error. There's not one there actually, but we'll start with the top cell. The error divided by the number, and we square that. Put another set of brackets around it because we want to add it to the other number that we're dealing with, which is the velocity, and the same with that, we want to take the error, divide it by the number, square it, and then so make sure we got right brackets, and we want to take the square root of the addition of those two quantities. We can just check that that's working. We've got no errors with the brackets. And then we need to multiply that fractional error by the resultant quantity. The resultant quantity is the actual discharge, and we're multiplying that by all of this. We put brackets around that. Okay. Once where it's division by 0, you might as well just delete them. So we now have the discharge, the sum of the discharge, and then we also have the error. Now we need to sum the errors in order to have an error that goes with the sum discharge. Summing errors, we square errors and then add them together and then take the square root. The easiest way of doing this is to actually have another column in which we can actually do the square of the error. So we'll square that. There's all our squared errors, and then we can have in here the sum of the squared errors, and we can take the square root, which is raising to the power of 0.5. And make sure we're working to 3 decimal places, so I've formatted that to 3 decimal places as well. So we've got a discharge of 0.31 meters cubed a second, plus or minus 0.04 cubic meters a second. In litres, that's 310 litres a second, plus or minus 40 or 41. Okay, so you need to do the same thing with the other 2 sets of data. You just need to fill in the average velocity and the error with it, and the discharge, which is the multiplication of the velocity and the area, and then work out the errors. And then they'll appear in this little table here, giving you the 3 discharges, and you can get the average of those 3 discharges and the error on the 3 discharges as well. So you've got an error actually within the method, and then you can work out an error between the 3 times when the method's been used, and that's the standard error, which will be this number. And then you can compare that set, which are the flow metering discharges and errors, with those from the dilution gauging. It's worth plotting these graphs up, well, they're plotted up for you, but looking at these graphs as well to see how comparable the sections are.